So in today's school, we looked at electron configurations. So we said the electron configuration, that is the one that you guys learned in Zambia, and the electron configuration that you guys are going to learn, let me not say in Morocco, but wherever you're going to go, that is going to deal with sub-electronic shells. We are going to look at it in this way. You have sub-electron shells, that is the S, the P, the D, and the F. Now, each of them occupy a maximum number of electrons. So in the assignment that I gave, the assignment was, how many electrons does each occupy? Is it the S orbital, the P orbital, the F orbital, and the D orbital? How many electrons does each occupy? So we found out that 2 electrons are always occupied by the S orbital, 6 electrons will always be occupied by the P orbital, and 10 electrons will always be occupied by the D orbital, and 14 electrons will always be occupied by the F orbital. So now, with that in mind, this is where we started our configuration électronique. So I gave a few examples. I told people to give elements that they would want us to configure, so that it shouldn't be an example that I'm going to come up with, no, but it should be an example that you guys would want to see being applied. So we had examples like fluorine, we had sodium, we had manganese, no, we had calcium, potassium, nitrogen, argon, and sulfur. Yeah. So I'll just share a presentation of what we did in the morning. I'll explain maybe for 2 elements, then we build up on that one. Yeah, maybe like that to be helpful. So just a minute. So we said we are going to look at the periodic table, that is top 20 elements, the top 20 elements. So we had a few examples. So we had lithium, beryllium, we had fluorine, sodium, potassium, calcium, nitrogen, and argon. So I'll start with the first 2. So we were saying the rule that we're going to apply when occupying these energy levels would be that it's called the règle de construction, or bien règle de Klossowski. Now, we are saying the rule would be that each energy level is going to occupy a maximum number of electrons. So the energy levels in Zambia, you guys call them K, L, M, and N. K, L, M, and N. Now, these are energy levels, like just normal energy levels. Now, the energy levels have subatomic shells. Subatomic shells. So if it's an L orbital, it has a subatomic shell, that is the S and the P, the S and the P. If it's the M subatomic shell, it also has the S and the P. If it's an N or N energy shell, it also has the S and the P and something else also. Now, for the where I'm not mentioning, where I'm saying something else, there's an exception. There's what you call the D, the 3D. So this is where I'm supposed to now start explaining for this afternoon. Yeah. So these are the energy levels that each of them have. Now, we are calling them A, K, L, M, N. This is what we were calling them in Zambia. Now, each of them is made up of sub-shells. That is the 1s, 2s, 2s, 2p, 3s, 3p, 4s. Now, I said lithium will be our example, the example we're going to consider now. Lithium will be our example we're going to consider. Lithium has an atomic number of 3. Now, the electron configuration that you guys learned from back home for lithium would have been 2, 1, isn't it? It would have been 2, 1. So now I said, for those that were here in the morning, I said, what we do is when you're arranging or doing your configuration, you say 1s, and you go there like a 2s, 2p. So lithium has a maximum number of electrons, that is 2. Now, how many electrons are occupied by the s orbital? Maximum, it's 2 electrons. So we are going to fill in the s orbital with 2 electrons. Then how many is supposed to be occupied by the s orbital? It's supposed to be 2. That's the maximum. Now, in our case, we are already at 2. We're already at 2, like we have already exhausted 2, and there's only 1 remaining. And therefore, we are going to have a 1. Now, the 2p will not be occupied because there is no electron to occupy this shell. And therefore, the electron configuration for lithium would be, the electron configuration for lithium would be 1s2 and 2s1, which is the same as, for those that were there in the morning, which is the same as 2, 1, which is the same as 2, 1, which is the same as this configuration that you guys have learned all the way back from Zambia. Now, there's also another notion that I came up with. I say the notion of configuration électronique avec les gaz rares. So it's a noble gas electron configuration where you use a noble gas to represent an electron configuration. So the question that I was asking the people that were here in class in the morning, I was like, what noble gas is this? What noble gas is this? So they define this noble gas to be helium because it's only helium that has 2 electrons in the outermost shell and respects the octet rule. It's only helium that has 2 electrons in the outermost shell and respects the octet rule. And therefore, I also said that the electrons that you're going to find at the far end for any atom, like lithium here, the electron that you're going to find at the far end is what we are going to call the valency electron. The valency electron is the one that is responsible for either the gain of electrons or the loss of electrons. In other words, the valency shell is responsible for the formation of ions, because we understand to say that an ion is formed when there is an increase in the number of electrons that is caused by gaining, and when there's a decrease in the number of electrons that is caused by loss. So the valency shell will always be the one at the far end. I think you guys have done this. The valency shell or the valency electron will always be the one at the far end. So in our case, the valency shell is this here, the 2s à la puissance 1. Therefore, the configuration électronique will not, avec les gaz rares, we are not going to consider the valency electron, but we are going to consider the configuration électronique of the one that precedes the valency shell. Now, in our case, this here represents the electron configuration for helium. So the electron configuration for helium is 1s2. 1s2. Unfortunately, helium cannot be represented by any other noble gas configuration because it's the only noble gas that has maximum of 2 electrons outermost shell, and it cannot be represented by any other. Yeah. So the first shell occupies 2 electrons. That is for helium, and that is why we have this representation here. So in other words, this helium here in square brackets just represents this 1s here. The helium in square brackets just represents the 1s2 for the configuration électronique for lithium. So before I allow a question, I will just add on with another example. So we also looked at examples like fluorine and sodium. So we said fluorine has an atomic number of 9, and the electron configuration that you guys have learned from Zambia was 2,7. 2,7. So like I said, the strategy will always be 1s, 2s, 2p. By the way, we call this the Mutale method, where we use the principle or the notion that an electron in the s orbital will always be 2, that in the p will be 6, in the d it will be 10, and hence the suite. So there's also the periodic table method, but for the periodic table method, I won't go in depth for the periodic table method. You guys will look at it in the video. Yeah, but for now, this is how you do the electron configuration. So we're saying how many electrons are occupied in the in the s orbital, maximum it's 2. How many are occupied in it's 2 in the other s orbital? That's going to be 2. Sorry, 2. And the p orbital, we're going to have how many? 6. Number, if you add everything here, you say 2 plus 2, you're going to have how many? You're going to have how many? 2 plus 2.
You're going to have 10.
2 plus 2.
4.
Plus 6.
10.
You're going to have 10, which is not in accordance with this here. The number of electrons that fluorine has is 9. Therefore, it's going to be 5. So what I told your friends in the morning, say, it's the same thing as the electron configuration that you guys have learned over the time from Zambia, which is 2,7. It's the same thing. Now, how do we know that it's the same thing? We said the 2 that you guys are saying, that the 2 there, the 2, 1s2. Then the 2s2p5. This is what you are seeing there as your 7. I'm not saying, okay, I'm not saying when you do your configuration you're supposed to add, but I'm just saying this to give you some, at least enlighten your understanding. When you say 2,7, 2,7, when you represent the electron configuration in the form of the SPD, Configuration Électronique, you are going to have 1s2, 2s2, 2p5. And this here will be equals to, it's the same thing, c'est la même chose. It's the same thing as 2,7 that you guys have learned over the time. Now, I also stated to say that the valency shell will be the one at the far end. It will be the one at the far end. Now, we are saying that this here you're seeing here, 2s, 2p, is a shell. It's a shell. The 2s, 2p, it's a shell, and its name is called L. The 3s, 3p you are seeing here is called M. It's called M. So M, in other words, is made up of 2 subatomic shells. It's made up of 2 subatomic shells. Therefore, in our case here, we have a K, and we have an L. We have an L there, which represents this, and we have a K, which represents this here. So now, what's our couche de valence? Couche de valence will be this here, because this L is the highest energy level that we have for fluorine. It's the last energy level we have for fluorine. And the L is made up of 2 subshells. That is the 2s2 and the 2p5. And therefore, the electron configuration that is for the noble gas would be this here, like we said in the earlier example, is the configuration for helium. This is why we have the helium in square bracket. And please, all the time you have the noble gas electron configuration, you use the helium, you put the noble gas in square brackets, you put the noble gas in square brackets. Then you have helium, and you have this here, which is the couche de valence, which is our L. Couche de valence, which is our L. Now we went further on, we looked at sodium. So we said sodium has 11 electrons, or protons. Now its electron configuration is, d'après la méthode de Zambie, it is 2,8,1. 2,8,1. And if this is the electron configuration that is for sodium, we are going to apply the Moutale method, which is 1s, 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 2s, 2p, 3s, if in the case of a 3s, or bien 3p. So we are saying the maximum number of electrons that the s orbital is supposed to occupy is how many? It's 2. For the s, it's going to be 2 encore. For the p, it's going to be 6. For the s, it's supposed to be 2. But now, you find that if you're to calculate the number of electrons, if you're to add all of them, you say this is 2 plus 2, that's 4. 4 plus 2, you're going to have a 6. 4 plus 6 is 10, and 10 plus 2 is 12. It does not sum up with this here. It does not sum up with 11. Therefore, you are going to have 1 electron there, and there is no more electron that is going to occupy the 3p. And the electron configuration for sodium, that is the SPDF electron configuration for sodium, becomes 1s2, 2s2, 2p6, 3s1. And the couche de valence in our case does not become 2s, 2p, 2s2, 2p6. It is 3s1. 3s1 is our last orbital. You can also look at it from here. We said the first orbital is going to be called K, the second one is going to be called L, third one is going to be called M, and the last one will be called N. So we have K, L, and the last one, M. So our couche de valence in this case becomes 3s1. Now, if we're asked to give la configuration électronique d'après les gaz rares, which is a noble gas electron configuration, we are going to consider this here. You are going to consider this here. Please take note, always when you're looking for the configuration électronique for the gas rare, always, first of all, look for which one is your couche de valence. Look for your couche de valence. Then at the end, whatever remains, just count the number of electrons and look for the noble gas that has the equivalent number of electrons. In our case, if you to count, you're going to have 2 plus 2, that's 4, 4 plus 6, that's 10, and the only noble gas that has 10 electrons on the periodic table is helium, neon. It's a neon. And therefore, neon in square brackets 31s, 3s to the power 1 will be the configuration électronique for sodium. So the neon in square brackets just represents, c'est la même chose. You can either write it in this way, or you can write it this way. This in green here is just showing that this is neon. This here is neon. Maybe if I can just do this also, so it can suit. So the green here and the green here just represent the same thing, but it's just an écriture abrégé. It's an écriture abrégé, some sort of shortcut that you can use to configure these elements. So for those that were not here in the morning, is it clear? Is it making any sense? Is it making any sense?
Yes, it's making sense.
Okay, so we can now start today's school. It's the same thing with the same examples here. Potassium, c'est la même chose. Maybe I give an example on potassium, then we start today's school. So potassium's electron configuration d'après la méthode des zombies was 2,8,1, 2,8,8,1. So now using Mutale's method, it will be potassium, and I said something, I told these guys that every time you're giving a configuration electronic, you also put a symbol and you use the atomic number so that it guides you. So we're saying 1s, 2s, 2p, 3s, 3p, 4s, we end here. So we are saying the maximum number of electrons that the s orbital is supposed to occupy is 2. That for the s orbital on core is going to be 2. It's going to be a 2. For the p orbital, it will be a 6. For the s encore juge, for the p, it will be 6. And for the last one, we are saying the maximum is supposed to occupy is 2. But in the case where you sum up everything, you find that it does not add up with the configuration electronic that we are supposed to have here. This is going to be 2 plus 2, 4 plus 6, 10, plus 8, 18. 18 plus 2 gives 20. Now, we do not have 20. This is potassium 19. Therefore, it becomes à la puissance 1. Now, The question is now, what would be the configuration?
The question.
Yeah.
Okay. How many subshells are in the third shell?
In the third shell, there are only two.
Yeah.
There are only two. Like, okay,
Not three.
K. No, just a minute. K. L. Is it L? L. No, I know where your question is coming from. It's actually in the fourth shell where you have three subshells. You get it? It's actually L. It's actually in the fourth M N. In the fourth subshell, this is where you have three. Oh, in the N will be at the fourth energy level. This is where you have three subshells. In the fourth, not the third, in the fourth. So this is the reason why for the coup I gave in the morning, I only went as far as 20. But for the coup I'm going to start giving now, I'll go as far as pen and pot. So the first 20, I can get you.
There's a certain video I watched on YouTube, but the people are saying that the third shell has three subshells, which includes the D shell as well.
3D.
Yeah, the third.
No, as in, okay. The video there was just trying to explain maybe the progression of how the shells will go in line with the quantum numbers. I'll show you this. There's another presentation I'll show you with a PowerPoint that I have for the coup. It's just a representation to show you that, okay, the numbers will be, it's an order because it's going to be 1s, 2s, 2s, 2p, 2s, 2, 2, 3, sorry. It's going to be 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4. It will continue like that. You even find that there's 4f, you go to 5f, 5d, all those things. It's just a progression to show you that in the progressing quantum numbers, you are going to have this type of arrangement of shells. But in our case, for the top 20 elements, we are only going to have a maximum of this is for the first one, the K, you only have 1. For the L, you only have 2. For the M, you only have 2. For the N, this is now where now you are going to have the D. For the N, you're going to have the D. So for the top 20 elements, from hydrogen to calcium, this is how you do it, from hydrogen to calcium. If you understand how you do it from hydrogen to calcium, the next ones you won't have problems. The next ones you won't have problems. So now, I can continue. I'll address your question. Don't worry, I'll address your question because this is what I'm going to do in today's school. Yeah. So this here, if you're to calculate, if you're to count all of it, you're going to find that this is actually a noble gas. And this noble gas here, when you count, this is going to be 2 plus 2, 4 plus 6, 10 plus another 8 is going to give 18. And the noble gas on the periodic table that has got 18 electrons is argon. And this is where the argon in square brackets comes in. And the valency Cauchy is at the far end there. It's at the far end. It's at the far end there. Yeah. Then maybe another thing I told these guys to just remind me of was, what if potassium forms an ion? What if potassium forms an ion? How are we going to represent this configuration? It's very simple. What it do is, what happens to potassium when it loses an electron? When it loses an electron, you just forget about this. You get it, eh? Is it clear?
Yes, it's clear.
When potassium loses an electron, it loses this one, TEF. It becomes a noble gas. TEF.
Yes.
So it means if I was to give potassium as an ion here, I'll just remove this and put 0 here. Kwapwa, this is for potassium ion. Potassium ion, same applies to the noble gas configuration. It would be 0 like that. Is it clear? Then nitrogen, same principle. If nitrogen forms an ion, we are going to, how many electrons does nitrogen lose for it to become an ion?
One.
Huh? How many electrons? Nitrogen is what? Noble. Is it a metal or a non-metal?
Doesn't it gain?
That's the question. Is it a metal or a non-metal? If you answer this question, then we know our direction.
It's a non-metal, so it has to gain 3.
Then how many electrons is it supposed to gain if it's a non-metal?
3.
Exactly. So 3 more electrons. Therefore, the configuration would be n à la puissance quoi? À la puissance quoi? C'est pas what? How many is it gaining?
3.
Guys, it's like muy opogamba man, say. When vovuta viogani vinan vishimi. Which one between the chemistries that you guys are learning? Which one is hard, eh?
Biochemie.
Bon, what about chimie organic? So it would be 1s 2 that is 2 2s 2p. So we are saying here you're going to have a 2, and it has gained how many? It has gained how many? 3 more.
It has gained 3 more.
Therefore, it will be à la puissance 6. À la puissance 6. So this here is a noble gas. This is a noble gas. Which is the idea? Which is the idea? Because elements on the periodic table will always want to gain or lose electrons to satisfy the octet rule. So when I say octet rule, it's that rule that you guys were learning, say they always want to be in stability. That's the octet rule. That is the octet rule. Elements will always want to be in atoms, will always want to be in the stable arena, stable form. So we have 2 plus 2, that's 4. 4 plus 6, that's 10, and the noble gas at 10 electrons is a neon, like that. So this is our element that nitrogen forms when it becomes stable. Yeah. So this is what basically happens with electron configurations when you have loss and gain of electrons. Same applies to sodium or calcium. You lose, it will have 0. It also have 0 like that. C'est clear?
Yes.
Okay. So now we address Mr. Who's this? Mr. Bless's question. So that was the rule. That was the rule that you guys were applying. Now, here are some exceptions. Now, hope it was clear for the first part. Now, here are some exceptions. Now, this is where Mr. Who's this rule comes in. So you see what I was saying? Eh? So this is the, oh, sorry. Now you can see, Tef. You can see?
Yes.
So first of all, before looking at this, I want you to start from this side. First of all, start from this side. Okay, so l'energie energetic. Okay. So we're here. So look at this side first, then we come to Uku. The rule is, this is how you're supposed to fill in the shells. This is the order in which you're going to fill in these shells. You're going to start with 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. Now, what Mr. Blaise found on the internet was this here. This, what you're seeing here. It was a progression of the quantum numbers and the energy shells that are attached to those particular quantum numbers. So you have the 1s, second s, that is 1 second, that's 2s, 2p. Then for the quantum number 3, you have 3 shells that have the quantum number 3, not sub-energy levels. You have a quantum number 3, n is equals to 3. And the quantum number 3 has got 3 subshells. It has 3 subshells. There's what you call the S, the P, and the D. There's what you call the S, the P, and the D. But when you're filling in, when you're completing, when you're doing in la ordre, the construction, when you're constructing these configurations, you don't go 3S, 3D, 3P. No. The order is like this. You start with 1S, you come to 2S, you go to 2P, you come to 3S, you go to 3P, you come to 4S, you come to 4D, 3P, sorry, let me start afresh. You start with 1S, you come to 2S. You go to 2P, you come to 3S. You come to 3P, you come to 4S. You come to you come to 3D and come to 4P. From 4P, you come to 5S. 5S, you come to 4D. 4D, you come to 5P. 5P, you come to 6S. 6S, you come to, 4F. 4F, you come to 5D. 5D, you come to 6P. After 6P, you come to 7S. 7S, you go to 5F. 5F, 6D. 6D, 7P. 7P, you go to 6F. 6F, 7D. 7D, 7F. So now this is where the exception comes in now. This is where the exception comes in. So the top 20 elements, I set it up. Where is this? Top 20. Top 20. Top 20. This, just this. The last shell for the top 20 elements is going to be 4S. Is it clear with a regular deconstruction before we start doing exceptions? Is it clear?
Yes.
Okay. So here are the exceptions now. Okay. So we'll do a bit of, so we'll do chromium. We'll do, I've also got some examples. I've got cobalt, I've got selenium, silver. I think these ones will be helpful. Then when we are done, please remind me, just someone, when I'm done with these 3 examples, someone should just say, Kaz can tick. So I'll start with cobalt, that is 27. Then go to selenium, that is 34. Then I'll come to the last one, that is going to be silver. Let's hope you guys have periodic tables. Silver, that is 47. 47. So the same principle. Now I want you to follow bueno, slowly but sure. Slowly but sure. So maybe to just give some more light, I'll get the periodic table from the internet so that we go together ensemble. Because I'm pretty sure you guys are asked questions on electron configurations. You are asked questions on electronic configurations. So we'll do this. Can you see the periodic table now?
No, I can't see it.
Eh? There's no periodic table.
I can't see anything. I can only see exceptions or grade the
I've not said. Oh, sorry. Can you see it now?
Yeah.
Yes.
Okay, well, I didn't share. Sorry, I didn't share. So we're going to look at 3 examples. These 3 examples, s'il vous plaît, suivez avec moi. Doucement. Doucement. So, la règle de construction, we said it's 1s, 2, let me write it across, wiser. So say 2s, 2p, 3s, 3p. Now, Mr. Blair's question was, the third shell is supposed to have the D. D'après la règle de construction, it shouldn't have the third D. Why? Because when we are filling in the energy levels, that's why I said, when we are done with this part, someone among us, I don't know if you're going to write it down, but just remind me to say, just say case quantique. I will know what to do when we get there. Case quantique. So, d'après la case quantique, I'll just explain a bit. We have energy levels, succession of energy levels. Those 2 lines that you guys we are looking at in Bohr's theory, those are the things that we're going to look at now. How to fill in. It's the same now, it's just that it's a diagrammatical representation of what we are going to. So it is found that the 3s and the 3p are in a lower energy as compared to the D block. It is for this reason why the exception comes in. It is for this reason why the exception comes in. The energy levels are in different states. They are in different states, even if they have the same quantum number, but their energies are in different states. So instead of it being 3D, we're going to have 4s, because the s orbital has a lower energy as compared to the D orbital. So we're going to have 3D. This is where the D comes in. Then we are going to have 4P. Hope it's making sense. So now, the reason why we have an overlap, the reason why you have an overlap here between the, is it the 3P and 3S? The reason is, when you compare the 2 energy levels, the S and the D, or maybe let me say the S, the P, and the D, the S and the P in reference to the D, it is found that the D orbital is found at a higher energy as compared to the S and the P orbitals. Now, in life, even in general principle of life, a human being will always find the easiest route out in everything. The human being will always find the easiest route out. That's the same principle that these electrons will take. Other than going to the D orbital, they will rather go to the S orbital. Why? Because it is found in lower energy as compared to the 3D. Same applies to the P, the 4P here. It will occupy the D and later on go to the P. It will occupy the D and later on go to the P. Now, there's another thing you're supposed to take into consideration. I'll write something here. That is Untitled Rule, which is a SP, D, F, no, G. What comes as P, SP, D, D, F, huh. So, Muntale, how many does S occupy?
2.
Then P,
Occupy 6.
D,
10.
F,
14.
G. So
I don't know G.
So it goes as far as
But I'm sure you just add 4.
Okay, so it goes as far as the F. Everything we're going to be doing will be based on this, please. It will be based on this. Nothing else, nothing more. Just this. Now, I want you to just follow me. We know. Do small, just calafin. So cobalt has an atomic number of 27. Has an atomic number of 27. Now, with what Mutale has told us, how many electrons is the S orbital supposed to occupy? Maximum. TNI. Maximum. How many?
2.
Okay. So 2 S
2.
P
6.
S.
2.
How come it's only Mutale that's answering? P
6.
S
2.
2.
D
10.
10.
P.
6.
Okay. Voila. Once you've done this, you are okay. So you're saying it's supposed to occupy 6. So what I advise you guys to be doing is, I don't know if in your exams you'll be given periodic tables, but I at least you guys should have a visual perspective of how the periodic table looks like. Cobalt is a transition metal, so it is found in those, the D, and the F. Also, for those guys that were not here in the morning, so we said the periodic table is divided into blocks. The periodic table is divided into blocks. There's this block here. There is this block here. There is this block here. And there is this other block here. So this one here is called the S block. This is called the D block. This is called the P block. And this is called the F block. So another thing about the periodic table that you guys have learned so far is that each period can help us find out how many energy levels that an atom is going to have. So take, for instance, sodium. Sodium has an electron configuration of 2,8,1. And how many energy levels do we have? We have the 2, we have the 8, and the 1. And therefore, it is found in period 3. So 1, 2, and 3. So the electron configuration we're saying is 2,8,1. So with this, we can also find out the period in which each of these atoms is found in. Potassium is 2,8,8,1. That is 2, number 1, 8, number 2, 8, number 3, and 1, number 4. And it is found in period number 4. Period number 4. Period number 4. So these, for those that were not there in the morning, I showed a way you can use the periodic table to find the electron configuration. But for now, I won't go much in detail about it. We're just going to use the Mutale method. Now, cobalt is found at position number 27, and that's the atomic number. Now, we are saying it's 4 o'clock. It is found in the D block. It is found in the D block. Nothing else could P. Nothing else could P. And therefore, another thing that you can also look at when you're doing these configurations is just count the number of electrons. Just count them. When you count them, you'll find out that, okay, some are excess, some are okay. So let's count. 2 plus 2 is how many? 10, 10, 10, 10. 2 plus 2?
4.
4 plus 6?
10.
Plus 2?
12.
Plus 8? This is 8.
20.
Plus 10?
30.
So, not we're already out and we have 27. So, A, we cancel it. It won't work. Now, at 10 here, we have 30. When you just count for this, you have 30. Now, for us to have the correct number of electron configurations that will satisfy cobalt, how many are we supposed to reduce? How many are we supposed to reduce?
3.
So, you're bashing up. 3D, cha?
7.
Voila, 3D, 7. So, the exception here is whenever you are doing your configuration électronique, s'il vous plaît, s'il vous plaît, s'il vous plaît, hein? S'il vous plaît, because these are the questions that they bring for my exam. This is what you're supposed to do. Please, s'il vous plaît. I will come back up so that we. Please, can you see this sharing? Can you see this sharing?
Yes.
La règle,
Yes.
la règle de construction, ou bien Afubau's principle. The order in which you're going to occupy these electrons will be, you start with the 1s. Look at these two arrows, eh? 1s, you come to 2s, 2p, 3s, 3p, 4s. Then the exceptions now start. You have anything that is above to top 20, you have 3d, you come to 4p, you come to 5s. 5s, you come to 4d, you come to 5p, you come to 6s. From here, you go to, is it 4f? 4f, you come to 5d, 5d, you come to 6p, 6p, you come to 7s. 7s, you go to 5f, 5f to 4d, 4d, you come to 7p, 7p, you come to 6f. 6f, you come to 7d, 7d, you come to 7f. And it is concording with what we have learned so far, that the periodic table has only 7 periods. Am I lying? Which is the same, this thing you're seeing here, it's the same thing as this one here, these two arrows you're seeing here. So we have 1s, we have 2s, we have, from the 2 we come to the, from the 2 we come here, then we come like that. From here, from the 4s, 4p, instead of us going to the d, trace per 4s. Per 4s, we come to d. You say d, you come, that is the order. So these are the lines that you are seeing. These are the lines that you are seeing. So please take note of this order here. This order is very important. This order is very important because it's the one we're going to use for the I don't know if I'm going to call this a travaux dirigés. It's the same order we're going to use here. C'est la même chose. So this is the electron configuration for cobalt. So cobalt is electron configuration is this. Now there are cases where, okay, I'll come to that later. So this is the electron configuration with cobalt. Is it clear for everyone? Is it clear? Cobalt's electron configuration. C'est clair?
Yes, now I have a question. Do we necessarily need to memorize that entire table, or they'll give us what?
The periodic table.
No, not the periodic table, that table.
Oh, the Règle de Kleshowski, the one S2S.
Yes.
No,
Yes.
with time you get used. With time you get used. With time you get used. Trust me. With time you get. There's nothing even to memorize. Let me just show you what happens. On the periodic table, there is a fluctuation of energy. So I'll use the periodic table just to explain what happens, so that we fasten the course, so that you guys go home and rest. So what happens on the periodic table? That the first top 20 elements, the first 20 elements have got a very good energy variation. This is where now I come in with the Cas Quantique and all those things. Now, when you start on top 20, you start on top 20. I don't know if I can use, let me just look for another periodic table to just to give more light on what I'm trying to say. A minute. Okay, it's fine. Let me just use the same one. Let me just use the same one. Can you guys see? I'll just use the same one. I'll just use the same one. So it is found that the energy of the transition metals, some transition metals here, so the energy, as you start with scandium, which is number 21, the energy fluctuates. What I mean fluctuates is that if I say energy fluctuates, I mean the quantum numbers. Instead of, this is period number 4, this is period number 1, 2, 3, 4. So instead of us having period 4 for this one here, we are going to have period 3. Am I making any sense? This is 1, this is 2, this is 3, this is 4, this is 5, 6, 7. Am I making sense? Am I making sense? Because these ones are found here. Don't worry, these ones are found here. You only have 7 periods of the periodic table. So when energy, the energy levels here for scandium, Juska should be Juska, candium, scandium to candium, the energy levels fluctuate. So instead of you having instead of you having a 4D, you are going to have a 3D. Same applies here. Instead of you having a a 5D, you have a 4D. A 4D. Then for the lanthanides, you upper, you're in period number shan, you're in period number 6. You're going to have 5F. 5F. Then after 5F, you come back to 5D. Am I making sense, somebody? Am I making sense?
I can
But-
just see numbers. So
Yeah, in your exams, please, even wherever you go, they will never give you as far as the lanthanides. It's just to show you how the rule goes. So I've also given you an example, just show you how we can go as far as maybe maximum I'll go is silver. But if you guys want us to go to Helium, we can go to Helium. There's no problem. So the energies fluctuate. The transition metals have got an energy that is lower. When I say energy lower, I mean the quantum numbers. This is period number 4. 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 This is what we know. But with the energy that we are talking about, the energy fluctuations, this whole thing here is not period number 4. No. Period number 4 is only this one here. That is for potassium, calcium, and gallium to krypton. If this scandium here is found, okay, let me say it's found in period number 4, of course, but has an energy in line with the quantum number 3. It has a lower energy as compared to the P here, the P. Those guys that have done the periodic table method, you understand that, okay, before going to the, when you're moving from the S, you come to the D, then coming to the D, you go to the P. It's the same reason. The reason is the energy of the D block is lower than the energy of the P block. And therefore, I said in life, we always want stability. Therefore, it would mean electrons will occupy the D block, then later on go to the P block. So the energy fluctuations here have affected the quantum numbers as well. Instead of you increasing in the number of periods, like we're supposed to have 4S and 4D, it becomes 4S, 3D, then you come to 4P, you come to 4P. Then after 4P, you come to 4S. That's like a method that Mutale was asking if they're going to be giving you a table in the school. It's the same method. The method is 1S, 2S, 2P, 3S, 3P, 4S, 3D, 4P, 5S, 4D. Then you have what else? You have 5D, 5P, 6S. Now you have this one, 6S. You're going to have 5F, 4. No, you're going to have 5D. 5D, you have 6P. Wait, 6P. Then we are going to have 7S. Then is it 6F? Guys, 6F. Then no, yeah, 6S. So 5F. Then 6D. Then 7P. So 7P will be your last energy shell. It's the same principle as like a table. I'm just using the periodic table now to just help you follow through. So there is that energy fluctuation. There is that energy fluctuation. So even when you look at the example that I have here, selenium, where is it? Let me just show you. selenium. Selenium is at position number 34. So selenium here, we are going to have a fluctuation of the energies here. We're going to go in the D block. Then later on, we are going to elevate. We are going to go to the P block or the P energy shell. We are going to go to the P energy shell. So let's just do an example so that maybe it makes more sense. But so far, is it making any light, or it's becoming darker and darker?
Made light.
Okay. So selenium is number 34. So what I advise you guys to do for now when you're practicing, you can just write the Règle the construction 1s, 2s, 2p, like that would be easy. 3s, 3p, 4s, 4p. Oh no, not 4p, 3d, 3d. That then comes what? 4 qua.
4p.
Exactly. So how many electrons are occupied by, then not forgetting this here? Guys, it's like Mutare is the only one that is answering. Should I repeat? Is there any problems? So I repeat.
No.
Okay, ça va. So how many electrons maximum? It's 2. How many maximum? 2. How many maximum? How many maximum? Let's come by 6. How many maximum? How many?
Two.
How many? How many?
2.
How many?
10.
How many?
6.
6. So no, now with time, I don't expect you guys to go by 6. Then you come and subtract. Shanshan. With time, just know as you are progressing how many are left. So we have 2 plus 2, which is how many? 4. 4 plus 6 is 4 plus 6.
10.
So 4 plus 6, we have 10. We have 10. Then that's 10 plus 2 is how many?
12.
12 plus 6 is how many?
18.
18 plus 12 is how many?
30.
So in other words, guys, here's the secret. With a periodic table, it has been designed in a way that everything just sums up. We know of you. If you're to do the electron configuration for zinc, just zinc, you find that this is a configuration for zinc. This one, here, this one. This is a configuration for zinc. At number 30 is the configuration for zinc. For those that did the periodic table method, you understand to say, you just count, say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and zinc is found there. So it is the configuration for zinc. So whenever you have a 3D and it's occupied by 10 electrons, whenever you reach here, just know that it's already 30. When you just reach per 3D, just know per 20. When you reach per 4s2, just know that there's already 20 you've covered. You continue. There's already of counting. That's another maybe thing. What's happening? That you guys can follow through. So if this is 30, how many electrons are remaining? Normally, how many electrons are supposed to be added for us to have?
4.
Exactly 4. So now for those that did the periodic table method, we are going to count. We are done with the first 30. Then we are going to say 1, 2, 3, 4. And there is our selenium. So this is the 4 that we have there. Now, is it clear for Sion? It's clear? With
Yes.
seleniums, okay? So we go to silver, the last example, silver. So, même chose, Même chose. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. Then we have what? 5s. We have after 5s we have what? 4. For what? For quoi? For what? So these are the energy fluctuations I'm talking about. These are the energy fluctuations I am talking about. So how many electrons are occupied by each shell? So we have but let's hope at the end of the day, if you fine. How many for the s orbital? 2. For the s on core, 2. For the p, 6. S, 2. P, 2. S, 2.
P2.
D, 10. So how many do we have here? How many do we have already? How many do we have?
Excuse me, you've written 2 electrons on P.
Sorry, Mr. Chanda, sorry. How many electrons do we have for? How many so far? How many have you occupied? Huh?
30.
30. So how many are remaining? So we have 17 more remaining. 6. How many here? 2. How many here? How many? How many, guys? If this is 30, what is 30 plus 8? 38. So 38 minus this, how many are you supposed to have? How many are you supposed to have?
9.
Guys, namanti zona tikaziputa na zona. So we're supposed to have 9 electrons, which comes back to the method. Those that have done, there's what you call the periodic table method and the Mutale method. So with the periodic table, you count and say 1, 2, 3, 4, 5, 6, 7, 8, 9. And for sure, it's found at position number 9. Position number 9. Position number 9. So now, for the 3 examples I've given, are there any questions? Are there any questions for the 3 examples I've given? Okay. If there are no questions, now we look at la configuration électronique with what? With noble gases. But in my right, no noble gas. If we will do everything. So now the question is, before we even go to noble gas, the question I've always been asking is, which one is a couche de valence? Which one is the couche de valence for cobalt? Which one is the couche de valence? So that when we start up, we just go one time. Which one is the couche de valence?
Oui.
Which one is the couche de valence? Which one is the couche de valence?
4s, 3d, 7.
Voila. So now, if that's the couche de valence, what is the noble gas electron configuration? What is the noble gas electron configuration? I am asking a question. If that is the couche de valence as Monterey has put it, what is the noble gas electron configuration for cobalt?
Argon.
What did you say?
Isn't it argon? Then you add that. Isn't it? How many electrons are these? Isn't it 18 together?
So if it adds up to 18, if it adds up to 18, which one adds up to 18? Is it this one, or when we include this, the 2?
No, when you just start from the 1 into the 3p6.
Up to the 3p6 steps.
Yes.
Okay. So now
Wait.
the question is, there's a question.
And why are we leaving the 4s2?
This is where now the question comes in. The question was, what is the noble gas electron configuration? No, what is the couche? First of all, what is the couche de valence? Couche de valence. The last energy shell, what is it called?
See, 3d7.
The couche de valence is 4s3d. 4s3d is the couche de valence. 4s3d is the couche de valence. So if you remember very well from the example that I gave, let me just come back to this, what I wrote last time. 1s, what else? 2s, 2p, 2p, 3s, 3p, 4s. Now, for those that were there in the morning, I stopped here. Now, it continues. Now you're going to have the 3d and 4p. I stopped by S because that was as far as we are going to go. It was top 20. So we call this K, L, M, N. These are the names of the shells that we had. So, Mr. Samuel, the 4s3d, 4p is one shell. So there are M shells. So there are instances where I'll show you. There's an example here of what is it? An example of silver with 41, where you have to go to the other side of the periodic table, then you decipher which one is your noble gas. So the couche de valence here, the couche de valence is this part here. La couche de valence is this part, like Mutale said. Then this is our noble gas. This is a noble gas. Now, here's a question. Now, how would you know that this is our noble gas? How would you know this is our noble gas? The simplest method you would apply is you add these electrons, add them, as you are going towards the end. You add 2 plus 2, 6, 6 plus. Now, if you're a bit confused, which one is the noble, which one is the couche de valence, like Samuel is asking. If you're a bit confused, which one is it the 4s? Is it the 3d? Is it the 4s2 3d? You just count as you're going towards the end. So you say 2 plus 2 is 4, plus 6 is 10, plus the other 8, you're going to have 18. Now, if you add 2, you're going to have how many? You're going to have how many? You're going to have 20. You're going to have 20.
Yes.
Yeah.
Exactly. Now, the 20 that we have won't be a noble gas. You're going to have calcium. It won't be a noble gas. So 18 is the convenient one because 18 adds up to the noble gas that we have in question, which is argon. Is it making sense, Mr. Samuel?
Yes, it's making a lot of sense.
Okay, a lot. Bon. So it will be argon. So this whole thing here in red, in green, I will represent also this one in green to just represent that in argon. Even argon. Then we just add our couche de valence, which is a 4s 3d, and therefore this is our electron configuration, which can also be written. Some books write these configurations in this way. Can be written in increasing atomic or in increasing quantum numbers. What is this? Can also be written as a copy. C'est la même chose. Some will write them in this way. In increasing atomic principal quantum numbers, some will write it in this way. C'est la même chose, you people. C'est la même chose. C'est la même chose. Don't be surprised if you find a representation that is written in this way. Is it clear with the noble gas electron configuration? Then if it's an ion, how many electrons is it going to lose? The outermost shell is this, the 3D, that's the outermost shell. If it's going to be a copper 2 ion, cobalt 2 plus. 2 plus, it will be what? How many electrons? Come on, you guys, what's happening? Come on, you guys, what's happening? Namnaka. Huh? If it's a cobalt 2 ion, how many electrons is it going to have at the end?
Going to have 5.
SAF. That becomes the configuration electronique for cobalt ion. Cobalt 2 plus. So ainsi de suite. Now we go to the second example, selenium. So same principle, you people, same principle. Which one is our couche de valence? Which one is our couche de valence? Which one is our couche de valence?
Starting from 4s2 went out.
Okay, 4s2. So temperature pace upper
4s2 3d10 4p 4.
You guys, but Montare needs an award, and she's answered almost all the questions. Olobwanj, get us down, guys. So this becomes the couche de valence, and therefore the noble gas will be what? The noble gas will be what?
Argon.
Voila. Even very simple, guys. If argon, then you put the terminaison. Point. That's all. Then if there's an ion, also if there's a selenium ion, if it is now going to gain electrons, if it's going to gain electrons, selenium is in group what? Panama periodic table. It's a group what? Before I put electrons. Is it group what? It's a group what? I've put the periodic table there. It's a group what? Selenium me up. So it's in group 6 or group 16. So it's going to lose how many electrons? or gain how many electrons? 2 more electrons, and therefore we have stability. We have stability. So for the selenium, sorry, Yaba, we'll do this. We are going to say copy, cole, and this will be for the selenium anion. So we are saying the selenium anion has how many electrons in the outermost shell? It is supposed to have a complete shell. You're going to have 6. So for the selenium anion, you're going to have 6 electrons. 6 electrons. Sava? So far, so clear?
Yes, it's clear, but
Yes.
I don't know how you're picking the gases, the noble gas.
The noble gas, okay, the noble gas. So, Mr. Chanda, this is how we're making the noble gas, eh? So the noble gas is basically just counting the number of electrons. I'll show you when I'm done with all these. Just remind me on call. I'll show you the where, okay. It's just like a shortcut time. You see, in life, always go for the easy way out. So what we're just doing here is we're just counting, okay, say 2 plus 2 is a 4. 4 plus 6 is a how many? 10 plus 8, it will give us 18. Now, if we're to count to 18 plus 2, we're going to have how many? We're going to have 20. Now, we're saying at position number 20, that's not a noble gas. That's not a noble gas. So therefore, position number 18 will be the appropriate noble gas for our element. C'est clair? It will be the appropriate noble gas for our element. So this is where these guys are saying, no, it will be argon, because when you count this, it gives you argon. Or in other words, if you've noticed that, or let me just do this, maybe to just give you guys an enlightened explanation. What I'm just trying to do here is, pali argon up. I can put this. Pali argon up, I can do this. It becomes still selenium now. Okay, selenium shows with a 2 minus there, it gains electron. Obia, pali chonse, I can represent it with argon. Pali chonse, I can represent it with argon. So now the question you're supposed to ask yourself is, which one is our couche de valence? Which one is our couche de valence? So I said with time, you guys will be able to know that, okay, this is our couche de valence. This is our couche de valence. D'après, you're going to be using the same principle of this guy. Who's this guy? Alphabet, the construction, Kiloshowski. Now, for the 5th shell, it will be the same 5s. To be for 5s, then you go to 4d. 4d, you go to, is it 4f? No, you go to 5p. 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 Let's hope I've not forgotten one shell. For 5s. 1, 2, 3, 4, 5. Okay, yeah, we are still there. So this is correct. So for the 5th orbital, this will also be your couche de valence. But as you progress, A, B, C, D. So as you progress, you find that the couche de valence also increases. So maybe you might have 4, 5, say 6s, 6s. Then we have, is it 5d? Where is the 5? 5d. 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 Then you're going to have 4f. Then you have your 5p. Where is the 5p? 5, but 5p, like that. So as you increase shells, the none can also increase. So what I've just done here is what we are calling la règle de construction. That thing that Mutale asked if we are going to be given in exams, or maybe there's like a table. No, just like this, you will know that, okay, no, because there is energy fluctuation, please, on the transition metals, there is that energy fluctuation that you're supposed to take note. Because of that energy fluctuation, you always have energies moving up and down. So for transition metals from 21 to, is it 48, you are going to have that kind of transition, just like a one-step transition. Now for group 6, period 6, so period 6 to period 7, you have the double transition, where you have the 5D block decreases by 1, then you have the 4F, that kind of arena. But it's ce n'est pas très difficile. Is it making sense? Or maybe I should explain, but no. Is it making sense? But is it making sense?
Yes.
Is that Kasem Nankan? Please don't get confused. Don't be confused. It's the same table. C'est la même chose. Let me just go back to that presentation. Where is it? It's the same one. It's the same one. It's the same one. It's just that I have drawn it. I have drawn it in a different way. It's the same one. C'est la même chose. Each. C'est la même chose. Where is it? You go to the 4P, so 3P, 4S. 4S, you go to the 3D. 3D, you come like. C'est la même chose. You'll be moving up and down. And the energy fluctuations I'm talking about is, if you've noticed here, the 4S is in the lower energy. Now, when you compare the energy of the 3D to that of the 4P, the 3D is in a lower energy. Then the 4P is in a higher energy. Same applies to the 4D and the 4F. Now you have got the 5th orbital that is going to have that energy variation. So what I'm trying to explain here about the fluctuation of energy is what you are seeing here, the representation here. When I say energy fluctuation, this is what I'm saying here. Especially this part here, up. We are saying we're supposed to have a 4. From the 4, normalement, from the 4, we go to the 4P. Now, because there's an energy fluctuation, and we're saying electrons will always occupy the lowest energy possible. So before going to the 4P, we have to go to the 3D, then go to the 4P. So that's what I'm trying to say. Before we occupy the 3D, we are supposed to pass through before we occupy the 4P, we are supposed to pass through the 3D. That's the route. It's just like for you to go to Livingstone, you are supposed to pass through, is it Choma? You're supposed to pass through Choma. There's no way out. That's the route you're supposed to take. Unless you're coming from South Africa or any other country, but that's the route you're supposed to take. Is it clear? Est-ce que c'est clair? Mr.
Yes.
Mr.
Yes.
Chanda. Guys, like in Marema Norema Kupunzira Tefti. There's a question?
Tarema, boy.
Marema, nine Narema, guys, Muzi Bachap guy. But there's no way out. I have to finish this school. Because if I don't finish it, Mzaka na check school so ero Mzaka dandaola. You'll be like, there's always our time. Same there's a punzi that chevina. I thought. So we are done with this part. We go to the last one. So please don't forget to remind me on what do you call it? Kaz Kantik, eh? Kaz Kantik. So now in this case, which one is our couche de valence? Which one is our couche de valence? It's like who is this? Mutale, which one is a couche de valence? Like Mutale is the only one that is saying the couche de valence.
It's the 5S 4D. Oh, but starting from this one, like we have 1, 2, 3. This one goes to up to 4S 3D 4P. So this one 5S to 4D 9.
Voila. So it will be 5S 4D then Chapwa. So this one here is our couche de valence, like Mutale has said. Now we are going to count Onko to just verify what she says. So we are saying this is our couche Cauchy de valence. Cauchy de valence. So we're going to count. So how many is it you have? 2 plus 2. I said this is 30. In 30. 30. 30 plus 6. What's that? What's 30 plus 6?
36.
And we have a krypton there. We have krypton. So longer argon, we have a krypton. And therefore, la configuration électronique will be krypton with this Cauchy here. Like that. Voila. Voila. So when argon loses an electron, that is for the argon plus ion, we are going to have how many electrons? How many electrons? Guys, the electron zone vuta zona guys. Nikulema kwa bwanju. In who has taught from morning zone from 9. I'm still fit.
What's the question?
From 9. 8. Exactly. It would be 8. Someone was asking how long I've taught. After from 9, boss. From 9, just imagine. 9, 12, 15. So this is the configuration électronique for silver. It will be this. So from the 3 examples that I've given you, are there any questions? Are there any questions? Are there any questions? Okay. Okay. If there are no questions, now I'll just sum up. So please, 2 people to give me 2 elements from the periodic table. At least top 30. I'll accept top 30 for now because you guys want to rest. I also have to rest. Top 30. Just 2 elements. 2 elements. Top 30. A periodic table. Choose top 30. So apa, attends. La casa. Then just another thing that I'll add on would be structure the Lewis. So that because I failed to finish this school today, so it means on Severa Vendredi, inshallah, to finish the course. So I don't know if it's Zilax going to come in, but before finishing the course, I'll need people to. That's how you spell quantique. I need you guys to do an exercise for me. So you choose, yeah? Choose.
Ion.
Ion. Is ion on, if ion is on the top 30, we want to do it. Okay. Very lucky. Ion is number 26. So ion fer, number 26. So in French, ion is called the fer. Like that. It's called the fer. Huh? Another one. I said 2. I said 2. So that we save on time. Then another one. Please, another one. Top, just to, even choosing an element is not predictable. Eh?
Calcium.
Ashan?
Calcium.
Calcium. But guys, anyway, we're going to do them. Then I'll need top 10. 2 on call for top 10. Just 2 for the Lewis structure for the top 10.
Boron.
Okay, so we have boron. That is number 5. And what else? Oh, in French, boron is called bore. Bore. I ain't. But in my notes, I'm French. The response is I'm What else? Top 10, top 10, top 10.
Lithium.
Lithium, lithium, lithium. Lithium number 3. In French, it's also called lithium, like it. So, please, la case quantique, it's the same thing, hein? La case quantique, c'est la même chose. C'est la même chose. Now, I'll have two presentations. The first one will be for fer, and the second one would be for calcium. 20. So please, first electron configuration tapunzira kanani kan fer 1 S2 S P3 S3 P et quoi encore 4 S 3 D. Is it okay? I said top 30. Top 30, ça va. Top 20, we'll just copy and coller. So please, this is what you'll be calling diagramme énergétique, case quantique. C'est la même chose. So diagramme, because mzagamba ti nimuzibani, mzagamba no, c'est la position énergétique. Et énergétique, c'est ça où il spell énergétique. Anyway, c'est là, ça va aller. So, the configuration électronique for fer. How many electrons maximum? 2. Maximum, juge 6. Et 2. So we are saying ngatafika hapa ile paira 30 number of 26. So how many are we supposed to write hapa? (26 minus 30 shinga? Maybe if we do it like that.
4.
So you can even count 1, 2, no, it's not 4. 1, 2, 3, 4, 5, 6. 6. Okay. Is it adding up? Because this here is calcium, 20, and we need how many more? 6. So now adds up. So 6. Now, case quantique. So let's do for calcium as well. So that when we come, it's a so that is a how many? 2 upper shinga juge. Then we are going to have star. Then juge. Then star. Then how many? Juge. We are done for calcium. So la case quantique is just energy variations. The diagram I showed you guys is just the energy variations that we are going to look at. So now with the energy variations, that is, I don't know if these tables will be sufficient. No, let me do this. Okay, let me just draw the tables. It will be better like that. Have you guys seen these things before? Those that have done, what do you call it? Atomistic. Have you guys seen this before? Ishikubia na cha atomistic muno.
Yeah, wanavyoona hapo.
Ah. I told you guys, mkacha attend class ya Chimie atomistic mnakana tawe. Sankana cha base kunyumba. Anyways. So these two things you are seeing here, they can be represented. Sometimes some books will put in my boxes. C'est la même chose. C'est la même chose. Some books will put in my boxes. It's the same thing. So the energy variations, when I talk about energy, this is what I talk about. That fluctuation. Instead of you having, if you've noticed, maybe let me do this. What am I going to do? Fish. So as I'll be going up, I'll be explaining a bit. So the S energy shell and the P energy shell have two energy variations. They are different. So the S shell has a lower energy as compared to the 2S shell, to the 2P, sorry, to the 2P shell. So it will be on a higher energy. It will be on a higher energy. It will be on a higher energy. 2P, like that. Same applies to the other 3S. You're going to have a 3S, like that. And the 3S has, or in other words, the S orbital has a lower energy as compared to the P. You're going to have the P on top. So you're going to have a 3P. Then encore 4S. Now this is where the variations come in. We're going to have a 3D. Then the last one, which is the 4P, it's higher in energy. It's higher in energy, c'est-à-dire, on va le trouver en haut. Like that. Oh, P. So those that have done atomistic, if you were following the code very, very well, I know the people that have been doing atomistic here. Mr. Chanda, you've been doing atomistic, Tiff? Mr. Chanda, waenda bambozi. If you've been following atomistic very well from the beginning of this class, it's a time where I was explaining about the angular quantum numbers and how they come about and how the formula is applied, the n-1, n, all those things. So I will just talk about, what is that other part? The magnetic quantum number. The magnetic quantum number is very important because it shows us the orientation of the shells. The shells. So the S has the S is just 1. Now the P has an orientation in space. You are going to have you'll find people talking about 2px, 2py, 2pz. So this is called 2p, but this is called 2px, 2py, 2pz. Then Samuel asked the question in the introduction of organic chemistry. Say, no, there. So what is hybridization at? Is it DSP, sp3? So the same thing here. You have got these shells here. The shells also have names. You have got the DXY, the D. Is it DXY to the power 2, the DX minus? Those signify the magnetic quantum numbers. So in a book, when you're reading a book on quantum numbers and you find something like DXY or bien DX2 minus Y, they are just magnetic quantum numbers. They're just showing the orientation in space. I also showed you diagrams of how these orbitals might look like in space. Some look like spheres, some look like lobes, etc. But away from that, now what we're going to look at now is what we are calling Lacaze cantique or bien diagram energetique. Now the diagram energetique has got, is it how many principles? It only has one principle. Yeah, it only has one principle. Then we are using also Kleshowski's principle, the construction, principle de construction, which states that we are going to occupy an energy level that is lower in energy before occupying the other. Now, what Hans rule states, I mentioned about Hans rule later on, I don't know when it was, but I mentioned about Hans rule. Hans rule states that you are never going to occupy an energy level like this. You have, okay, let me not go to Hans rule. Let me first start with Kleshowski, then later on come in with Hans rule. Sava, is it clear? I start with Kleshowski, then go to Hans rule, so that it makes more sense. So if they tell us to now give a diagram energetic for this one, for ion, spin up, spin down.
It's 5 o'clock.
Satisfies this one, right? 2 electrons, 9 poor. Same up, spin up, spin up, spin down, spin up, spin down, spin up, spin up, spin up. Then this is where Règle, the hand, comes in. Whenever you're occupying energy levels, you occupy them with the same quantum number. Now, in this case, the quantum number that we are using is a spin quantum number. You always occupy them with the same quantum number, and if you're in the same energy, that's what you are going to do. Then later on, you come back now with spin down, spin down, spin down. Please take note, even as I am doing the spin down, spin up, I'm satisfying these things you're seeing here. I'm not just putting to my 2, to my shan. The 2 you're seeing here is the 2 you're seeing here, 1 and 2. The 2 you're seeing here is the 2 you're seeing here. The 6 you're seeing here is the 1, 2, 3, 4, 5, 6. Get 6 here. When I come to S4 to 3S, spin up, spin down. When I come to the 3P, so not pusher, 3S, spin up, spin down, spin up, spin down, spin up, spin down. So in other words, what you're going to do for all of them, if you know that you have 6 already like occupied, you just put spin up, spin up, spin up, spin down, spin up, spin down. Like when you get used with this, that's how you'll be doing it. Now for today, we are applying rules, so we respect all those rules. Then so we are done with the 3PS, 3P6. We come to the 4S, that is spin up, spin down. Now here, up and up. What you do is you go spin up, spin up, spin up, spin up, spin up, then spin down, spin down, spin down. No. 1, 2, 3, 4, 5, 6. Kalastapa. Kwana 6. Napitilira. Yakwana. Okay. So if they tell you in the exam, wherever you go, no, monsieur, mademoiselle, donnez-nous diagramme énergétique. So some people might represent this with my boxes. It's the same thing, you people. It's the same thing. Even if they put like a box, also yopa mkaenda kwa school, bakaenda a box ukatawe. It's a DMs and a ponzizo. C'est la même chose. It's the same thing. If I put like a box, it's the same thing. C'est la même chose. C'est la même chose. C'est la même chose. Then another question might be like, you know what I'm doing? I'm killing two birds with one stone, so that we have less work to do. Now the question is, what if the atom of what is element? Fer. It loses an electron. It loses maybe 2 electrons. How do you draw this on the cars can tick? How do you draw it on a cars can tick? So if it loses 2 electrons, it means apara bashinga apa. If it loses 2 electrons, it becomes Fe2+. If it loses 2 electrons, yala bashinga apa. It will be 4. And therefore, even the Kaz-Kantik changes. Instead of you saying up, Juska, you see, you'll be like, no, it has to satisfy this. So 1, 2, 3, 4. So we won't include this one because it has now formed an ion. Saf. Is it difficult? All you need to do, c'est pratique seulement. Is it clear? Even if, so I'll give an example. Maybe there was an element that goes as far as, where is it? Where's the gum? So maybe just enlighten, because someone might ask a question, say, okay, if we have a 10 here, then we have a 4s3, for example. Same thing. We're going to have our box. Please don't forget, Hans' principle is what you're going to apply. When you get familiar with this, you'll be just doing up, down, but in the accordance with the rules, you're supposed to go with up. That is 1, 2, 3, 4, 5, then come down. So down, ish. Down. So that's up, down, and down. Then how many you have? 3. So it's going to be up. Someone might ask you a question now, why aren't you going up, down here? Hans' rule will not qualify that. Hans' rule states if you have an energy level with the same quantum number, you distribute the electrons, you share them equally. The principle that states that share the little you have, you apply it here. You apply it here so that there is equal energy for all of them. So up. If there was another electron, it will come down. If there was another electron, now in our case, we don't have another electron. So is it clear with ion? Is it clear?
Yes.
It's clear.
Ah, guys, mushtamoshe mwe. Mushtamoshe. Sopo vingena, osati tikamba clear because mufuna enda kunyumba, no? Sopo vingena. Then, like I said in the call early in the morning, said the highest energy you're going to have will be positive 0, and the lowest energy you're going to have is a negative 13.6. Electron volts. Is Mr. Kundoni around?
Yes, I'm around.
Mangala maningizi bosses here, network. One.
In the back, so I haven't attended most of the lessons. So I congratulate you.
Okay. So, but let's hope if panga sense betting what it type.
Nafika pa point panga sense but.
Bon. So you can even do this one for me.
Yeah.
Alhamdulillah, alhamdulillah. Now, is it clear for everyone? Then now we are going to have 3s. Maka magelo. Is it clear? The girls, the ladies. Is it clear?
Yes, it's clear.
Yes, it's clear.
But my however, professor, the point of my guys. No. If you have a question, you ask the question. Then we're going to have the 4s. Which is the last one. So even to my boxes, to my dashes, c'est la même chose. C'est la même chose. So some books, it differs. The way people write these things differs. Some might prefer writing them just another attention. Some might write the first orbit, that is 1s like that, 1s like that. Then they would not respect the principle which we are stating to say that the energy levels between the S and the P vary. Between the S and the P, that is for the 2P, vary. They would rather just put them in the same line. Now, maybe to just give a justification to why they do that. They do that because they both have the same quantum number. They both have the same principal quantum number, which is 2. So they do not respect that the energies between the S and the P are different. But they just follow that, okay, no, they are the same quantum numbers. So there's no need for us to show that the energy is varying. So, if we're going to fill in this nankan, d'après la leg, the quoi, the hand is going to be up, down, not push oko, up, down, not push oko, up, 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 then down, down, down. So the même chose ici. This will be up, down, then so this there is gone, and that there is gone, and this here is also gone. That's up, down, up, down, up, down. And the last one is up, down. Then another question might be, what if calcium forms an ion? Calcium forms an ion, that's 2+. If it forms an ion, we are going to efface these 2 here because we will not have electrons there, and therefore this will be our configuration d'après la case quantique. C'est bon? Est-ce que tout le monde est d'accord?
Oui.
Alhamdulillah, alhamdulillah. Then we go to the last part.
Question. Yeah, this diagram, do we draw it on our own, or how is it in the answer sheet?
Oh, you draw it, boy. Oh, you draw it. Sorry, as in, I'm using the mouse, so the way it looks, it doesn't look presentable. Let me just go to the other side of the slide to just show you how the case quantique looks like. Let me go on Google, maybe if it's there. A case quantique. Case quantique. Cars can tick. So, no. Okay, I found one. Just a minute, I share. Maybe this one will work. Can you see the sharing?
Yes.
Yeah. So, like I said, some books will not respect the energies that each energy level, each subshelf, has. So they'll just rather write them like this. So you can start from, for as long as you show us the direction, for as long as you show us the direction of the energies, if it's going kumuluku, if you've noticed apa, ilia kumulu. Like energy showing that ilia kumulu. So for as long as you show us that there's that energy variation, so if you've noticed and they've not also respected E or the D, 3D. So for as long as you just show that the energy is going kuntansh, or if you are starting from the top and going down, but I advise to always increase in that order, increasing in that order. So you occupy the electrons, one, up, down, up, down, up, down, up, down. So you draw these things, you draw it. It varies. People have got different ways. Let me just look for another image, maybe to just where is there's also this one. You see, different representations. There's one there, some are written like that. So if you people have been following what I've been saying all along, so this is the K Kush, which we are calling 1s Kerekeshos, and this is the, what do you call it, the P, where you have the second Kush L, which have the 2s2 and the 2p6 da6 then same applies at the end. So this is another way of representing this. Then which one? Okay, something like this. So for ions also, if you've noticed an ion with one electron, that is the variation. Then I think that's all. So that we just do the last part and you guys are set. So is it clear, Mr. Gonan? As in representations, with representations, don't worry. It's not very difficult when it comes to representations. There are very easy representations. Yeah, it's just that my writing, the CDCM order. I'll show you even in the polycop I'm using. So now to close, is it clear?
Very clear.
Any questions? It's clear?
Yes.
Okay. So then to just close also, just wrap up everything now, we're going to look at structure, the Lewis. So Lewis structure is what you guys used to call, what do we call those things? Is it orbitals? I think it's orbitals. So now with Lewis structure, we always represent couche de valence. So here, we just use the Zambian configuration, which is 2,1 for boron. 2,
3.
2,3. For lithium,
2,1.
voila. So what it is with these diagrams I'm talking about is that we are just representing la couche de valence. The valency couche. That's what Lewis structure is. You are only using the couche de valence. I think you guys did this when you are doing ionic bonding in Zambia. There is a part, I don't know if it's in the key points, which says that when you're representing ionic bonds, it's important to just represent the outermost shell because it's the one that is involved in the energy gain and the energy loss. It's the same one. It's the same one. It's now the name has just changed. It's Lewis now. It's just a Lewis structure. So how you draw this one is you just draw a boron like that. Just draw a boron, say B. How many electrons does it have in the outermost shell? It has 1, 2, and 3. So how many electrons is boron supposed to gain for it to attain stability? Huh?
And 5.
Supposed to gain how many? Huh? Excuse me. How many is supposed to gain? How many is it supposed to gain?
5.
Supposed to gain 5. Dave,
Yes, 5.
so in a case where boron becomes an ion, we're going to have 5 electrons it's supposed to gain. And therefore, the Lewis structure for this one can be represented as just HB with my dots. So pa, pa, and pa. Then in Morocco, what they do is they just represent it with my dashes to just mean that there's there are 2 electrons there, so it can also be written as with 1 dash there, with 1 dash. Now with the other one, we can write it dash, but now the dash is not complete. It is not satisfying the octet rule. It is not satisfying the octet rule. So if boron now gained 5 more electrons, this would have been the structure for boron. This would have been the structure. So just another thing. Okay, yeah, better. So if it gained 5 electrons, that is 5 more, would have represented it as just the valency share. Why? 2, 2, 2, 2, which can also be written as B 5 Mwanza 1 2 1 2 1 2 1 2 like that. Now I'm gonna 8. Then how they also represent it here. So now I'm shows if they say 5 more. So the double liaisons, they just draw like a dash like that, like a dash like that, like a dash like that, and like a dash. It's the same thing. It's just that there's one there, there's another one there, there's one here, there's also another one there, there's one here, and there's another one there, there's one here, and another one there. So the shows this here, this here, this here is the same thing. They're all called Lewis structures. So same applies for lithium. Lithium will be L with only 1, 2, and with 1 electron. Then we are going to have 1, to which we are representing with the line T, like a lithium. Then this one here can be called a lone pair electron because it can be used for any other bonding. It can be used for any other interactions. Then if it forms an ion, that is if it gains some more electrons,
That is so.
about it.
Now on the same boron, this 5, is it representing the?
Oh, it's yeah. It's representing the number of electrons that we're going to get. I noticed that this 5 is going to bring confusion. It's just representing the number of electrons that it's going to gain. Sorry. I rub it time. Don't worry. I'm just representing.
I'm talking about the 2,3 we are using here. Are we considering the, since boron is in period 5 or is in group 5 and then period 2?
Boron is in group what?
Group 5.
Group 5.
Yeah.
Boron is in group 5. Group 3.
No, group 3. Yeah, group 3. Yeah, group 3, which means it's supposed to gain 3 electrons for it to be stable. Which means in the outermost shell, it has 5 electrons.
No.
Now where are we? We are this 5.
No. Boron is in group 3 of the periodic table, and it has 3 electrons in the outermost shell. It needs 5 for it to gain stability. Maybe now. Isn't boron one of the non-metals? Guys, is boron not one of the non-metals? How do you draw the staircase line?
Non-metal.
Come in the bunch. Come on, come in the bunch. Come on, watch it. Come on, go so. Come in the so. No go so. I don't know, I've forgotten how it goes. But boron is a non-metal. So it means it is going to gain 5 more electrons. Is it clear, Mr. Bliss? 5 more electrons. Or that method used to do in Zambia. Say this is group number 8. This is group number 8. Then what is 8 minus 3? So this is group 3. To find out how many electrons an element needs to gain. So you say, what is 3 from 8? You'll be like, it needs 5 electrons for you to gain stability. Is it clear? Est-ce que c'est clair? Mr. Blaise, is it clear?
No.
What's the query? What's the query? What's the query?
No, you can just proceed down. Yeah.
No.
Let me first just try to look through.
Oh, no.
I'll be able.
No, we can even look through together. No, we can even look through together. There's no problem, Mr. Blaise. There's no problem. There's no problem. We are saying boron is a non-metal, isn't it? Boron is a non-metal. So drawing the staircase line will help us now to just decipher that. Okay, just say, okay, no, boron is really a non-metal. So if it is a non-metal, how are we going to find how many electrons that boron needs for it to attain stability, for it to obey the octet rule? How do we go about it? So I showed you a formula that we're using in Zambia. That is, if you want to find out how many electrons an atom is going to gain or going to lose for it to attain stability, you will basically just subtract. You just subtract the group numbers. That is maybe group 8, because for group 6, you will be like, this is group what? Group 4. You'll be like, what is 8 minus 4? So this one needs 4 electrons. What is 8 minus 5? This one needs 3 electrons. What is 8 minus 6? This one needs 2 electrons. What is 8 minus 7? This one needs 1 electron. Then what's 8 minus 8? 0. It means these ones obey the octet rule. So now boron is in group number 3. If it's in group number 3, what is 8 minus 3? We are saying 8 minus 3 is 5. Therefore, boron has 3 electrons in the outermost shell. Boron has 3 electrons in the outermost shell. 3. Just a minute.
All right. Yeah, it's clear now. I was just thinking about something else.
No.
You can just proceed.
Okay, we can proceed.
Yes,
Hey,
we can proceed.
Guys, manajipisa maningi. Yeah, maybe I think you're thinking about those ones that do not obey the octet rule. Yeah, there are those things also. Boron is one of those guys that doesn't obey the octet rule. It only happens when boron is bonded with another atom. This is where now you have this kind of bizarre arrangement of electrons. But basically, Lewis structure, you guys, Lewis structure is the cross and dot structures that we learned in high school. That is Lewis structure. Now you're just representing it now without that you say why, without that you say just to my dots, pa pa pa. So this is for the ion. For the ion. In Morocco, they can just represent it with my dash so. So when you go to school and see to my dash, don't be surprised. No, c'est la police c'est so oui. C'est la même chose. C'est la même chose. So if there are no questions, please let me just share the last part that Kondwani might need. Can you guys see my sharing? Can you see it? Can you see it?
We can see what's written atomistic. There's something there.
Sorry. Guys, I'm not kazona, But you guys came late. Kubepetsa chita. Taponzira chabelo. Mabwera late. Tukomukaitina wazile. So to just close also, I just want to show you guys what we've done so far. So when you talk about Règle, when you go to school and they say Règle de Remplissage, it's the same thing as this one, Kleshowski's. I don't know if it's Kleshowski. Which this one? Where is it? It's the same one. It's the same one. If they say Règle de Remplissage, Règle de construction, it's the same thing. Don't be amazed. No, Stinapunzi, Shanshan. Same thing. Then energy diagrams. You've seen how people draw energy diagrams. Some draw them towards this side. Some draw them towards the other side. Is it clear? Est-ce que ça va?
Oui, ça va.
Okay. Then some might draw them with my boxes here. Représentation en case quantique. So règle de hand. So this is a règle de hand. Lewis structures, we have these ones here. Lewis structures, which we are just from looking at. So these two lines you're seeing here, they are double liaison. Then the ones that are not two lines, they are lone pairs. A lone pair is an electron that is not bonded to anything. So, or maybe it's not a pair, it's lone, it's alone. It's coming from the word alone. It's a lone pair. Yeah. So we have exceptions to the remplissage règle, which we looked at. This is l'inversion est identique pour sous-couche S, that is 5S, 4D, puis 6S, 4F, puis 7F, 5F, etc. So if they ask you for selenium to give the représentation électronique sur la case quantique, this is how you go about it. This is how you go. So yeah, so Kondwani, sometimes instead of you going with the energy diagrams like that, if you've noticed how they've represented it, it's just a straight line. with my boxes, jusqu'à la fin. Just a stretch to my boxes sphere, yeah. But I advise that you just draw to my energies that you're showing that you're increasing energy. Then Règle de Remplissage, we looked at what do you call them? Argon configurations. We also looked at say 3D, 4S configurations, ainsi de suite. Then configuration fundamental. So this is also when it forms, which is what do you call it? This is an atom of fluorine, Then the Lewis structure is so there are two electrons, and there's one lone electron there. So if it now forms an ion, when it gains another electron, this one will no longer be lone, it will be pair. It will be pair. Fluorine, wava, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So for it to gain stability, it needs how many electrons? Have I drawn the correct things first of all? I've not. It needs 1 electron for it to gain stability. So in the Moroccan, I shouldn't even say the Moroccan, no. The way this can also be represented, it can also be represented like this. With a star here, to just show that another electron has been gained. You get, which is the same thing as this. It's the same thing. Now you just put Kamua. That's the same things that you guys have learned from Zambia. Is it the dot and cross diagrams? Yeah. Then what do you look at also? Yeah, this is for sodium. So the argon representation there. And there is an exercise here. There is an exercise. So those that, no, for me, I don't force. So for those that want to practice configuration électronique, you can hit me up. I'll give you the exercise. Then later on when you're done, I'll also give you the responses. Yeah. So the next time we meet, that is on Thursday, we are going to end with this. With how molecules are formed, but basically just this part. This part. Geometry de molecule. That's this part. Yeah. I guess for today, it will be just like, I don't know. It will be just like maybe a 10-minute school. Maybe 10-minute school, something like that. So that I leave the rest for Monsieur MD to come and just add up 1 or 2 things. So, like I said, for those that want to solve this exercise, to just maybe improve on their configuration électronique, you can hit me up. You only go as far as question. Is this exercise? Is this exercise with answers? No, it's not the one. Yeah, it's this one here. This one. Just exercise 1 and 2. So for those that need some more, maybe more practice on these elements, please feel free to do them. So it says, donner la configuration électronique des espaces dans l'état fondamental, ainsi pour nombre électron de valence. So if they say ainsi pour the nombre électron de valence, this is where we come in with the noble gas configuration. The noble gas configuration. Yeah. So then, ainsi le nombre d'électrons de valence. Sorry. Ainsi le nombre d'électrons, they also want us to find the number of electrons in the valence. The number of electrons in the valence. So you give me, for those that will do the exercise, you give me the electron configuration, the normal one. Then you also give me the electron configuration, which is for argon, those things, the noble gas configurations. Then you give the number of electrons that are found in the couche de valence. Couche de valence. So if there are no questions,